Okay, hi everybody. So in this presentation, I'm going to be talking about small bodies and the early history of our solar system. In the previous presentation, I briefly mentioned that things like asteroids are interesting because they're thought to be remnants from the early solar system, from the very formation of this system. And what I want to do today is talk a little bit about why we think that's the case and use that as a jumping off point for some discussion of solar system formation models, specifically the solar nebula model. Okay, so what we've said is these objects, the asteroids in particular, which we have a lot of good pictures of, appear to be very ancient. Now, for the ones we've encountered, you can see why we would think that. They're heavily cratered like the moon or Mercury. But we actually can do a bit better than that because asteroids, as we've talked about, can reach us and land on Earth. Again, the Chelyabinsk meteor is a good example of that. There was a hole punched in the lake. At the bottom of that hole is a rock. This is a meteorite. This is a chunk of an asteroid that is now available for us to study. And it turns out this is a fairly typical one. These kind of objects are obviously of high interest, and they come in a couple of different types. They're generically called stony and iron for what they are made out of. Stony meteorites are made out of rock. Most meteorites are made out of rock, which makes sense. Rock is a fairly common thing. A large fraction of those meteorites have a very distinct texture. If you cut them in half, they contain these little spherical grains, which are called chondrules. These kinds of objects are called chondrites because they're made up of chondrules. The other 5% are actually chunks of metal, basically iron, hence they're often called iron meteorites. There is a small fraction which are a mix of both. These are very rare and are honestly some of the most striking objects you can see because they're basically a metal with little crystals of minerals embedded inside of it. Okay. And it's the chondrites I want to focus on first. The chondrites are interesting because rocks with this particular texture, or meteorites with this particular texture, appear to be amongst the oldest and least altered solid material in the solar system. Now, how do we know that? Well, we don't know that just by looking at them. This looks weird, but lots of rocks look weird. It is based on a study of the atoms in these things. Turns out that if you can physically sample the material, you can learn something about its age by studying certain types of atoms. Now, as we talked about before, atoms are composed of different parts. In the nucleus, there is protons and neutrons, and then surrounding those are the electrons. The electrons are negatively charged. They're held in place by the positive charge of the nucleus. And it's the interactions amongst the electrons that determine chemistry. So the chemistry is ultimately set by the positive charge of the nucleus, so the number of protons it has. And this is the basis by which we sort different types of atoms. Atoms with different numbers of protons have different chemistry and are called different elements. So carbon has 6 protons in its nucleus. Nitrogen has 7. And those two atoms behave differently. Now, in addition to having different amounts of protons, you can also have different amounts of neutrons. Neutrons are neutral particles. They don't affect the chemistry of the atom much, actually at all, really. What they do is just change the mass of the nucleus. And these are considered the same element. For example, these are both carbon because they have 6 protons, but because they have different number of neutrons, they're called different isotopes of that element. This is carbon 12, which has 6 protons and 6 neutrons, so 12 total nucleons in its nucleus. This is carbon 14, which has 6 protons and 8 neutrons. Now, this change in the number of neutrons changes the mass of the nucleus, which can be relevant. But what it can also do is change the stability of the nucleus. Carbon 12 is what is called a stable nucleus. It will never change its identity unless acted upon by an outside force. Basically, you would have to hit this nucleus with high energy subatomic particles before it would change. Carbon 14 is not stable. It is a nucleus that will, of its own accord, transform into another type of atom. Specifically, what happens is one of the neutrons, which is neutral, turns into a proton. Now, that turns something neutral to something positively charged, so it has to emit a negatively charged particle, an electron. It also emits something else called a neutrino. This is a transformation that happens in a very regular and predictable way that can be characterized in terms of either a decay constant or a half-life. And there are a number of different isotopes that do this of various sizes. There are isotopes of rubidium that transform into, say, strontium, and they have a different decay constant and a different half-life. Now, what these parameters are basically 2 different ways of looking at the same behavior. Turns out the rate at which these nuclei transform is fairly predictable and regular. The idea is if you had a pure sample of one of these unstable nuclei and you watched it for a year, the decay constant is just what fraction of that sample transforms. So if 10% of it decays, the decay constant is 0.1 per year, because that's the fraction that has changed. If it is 1%, then the decay constant is 0.01 per year. In practice, it's usually way less than that. Only a small fraction of the atoms actually change in a year, at least for the ones we're going to be talking about today. So that's something you can measure. You can imagine having a sample of the material and asking how much changes over a fixed length of time. The half-life is a related concept, but instead of saying how much of the material transforms in a fixed amount of time, it is saying instead, what is the time required for half of that material to decay? Now, that is usually shown using a plot like this. This is a plot showing how much of a given of an unstable isotope you have as a function of time. So we start off with a pure sample. So the surviving fraction is 1. And we have down here time in units of half-life. So below this purple region indicates the fraction that has survived. The blue region is the fraction of the material that is transformed, or also called decay. So the half-life is the time it takes this fraction of the material surviving to go down by a factor of 2. So only half of the material survives that long. Okay. Now, if you wait another half-life, the second one, then half of the remaining half decays, and you get a quarter. After 3 half-lives, half of that remaining half decays, and you get an eighth. 4 half-lives, you get a 16th. And you can actually calculate how much material is left as a function of time from this at any intermediate value. Now, these half-lives can be very long. For example, for carbon-14, it takes 6,000 years, roughly, for the amount of carbon atoms in a sample to decay by a factor of 2, assuming nothing comes in or goes out. Others are even longer lived, like uranium has a half-life of billions of years. Rubidium-87 has a half-life of 50 billion years, which is longer than the age of the universe. What I want to emphasize is, though, these are things you can calculate given a decay constant. Since you know how much decays in a year, you can calculate how long it would take for half of the material to decay. So it isn't like you need to wait a billion or more years to measure these numbers. You just measure how many decay in a certain amount of time. And for things with long half-lives, that fraction turns out to be very small, but it can be measured. Now, what's neat about this decay is very predictable. The rates at which these transformations happen don't seem to depend on the environment the atoms are in, which makes sense. The nucleus is very well shielded from anything in its environment because it's the electrons that interact with other atoms. Now, what that means is if we have a sample that has a certain amount of an unstable nucleus, we can predict how much of those nuclei will survive anytime in the future. We can also calculate how many more nuclei there were at any time in the past. So we could say, okay, 1 billion years from now, how many nuclei are there? 1 billion years ago, how many nuclei would there have been? Subject to the assumption that nothing was added or removed from that piece of material. That's a useful basis for figuring out age, but it's not everything you need. If you actually want to know the age of something, it's not enough to know how many of these unstable nuclei there is in there now. You also need to know how many nuclei it contained when it formed. This is the major challenge, and it's why people focus on specific unstable nuclei, because for certain types of unstable nuclei, you can figure that out. You can not only measure the sample today and say, it has this many unstable nuclei, you can also infer how many unstable nuclei it had in the past when it formed. Now, how does that work? There is a good example of that, which is used to measure the age of molten rocks, or rocks that were once molten, things that are coming out of volcanoes, basically. The particular isotope that's useful for this is a form of potassium called potassium-40. Now, what's special about potassium-40 is not its own chemical properties, it's what it turns into. Potassium-40 can actually decay in 2 different ways. In one case, one of its neutrons turns into a proton, emitting an electron. That turns potassium-40 into a form of calcium-40. But 10% of the time, it does something else. Potassium-40 captures an electron from its surroundings and turns one of its protons into a neutron. This turns potassium-40 into argon-40. Both of these are stable. So once this has happened, it's done. Argon-40 is special because argon is a noble gas. It is a gas that hates to form chemical bonds with anything. So it really wants to be a gas. In fact, argon is a significant chunk of our atmosphere. It's about 1% because it basically doesn't form chemical bonds with anything and filters out of rocks fairly efficiently. And in fact, it's very hard to keep argon in molten rock. If you have a fluid rock where all the atoms can flow relative to each other, if any of these atoms are, say, potassium-40, shown here in brown, convert to argon-40, they will rattle around, not make chemical bonds, and eventually reach the surface of the rock and escape into either the atmosphere or space. So when a rock is molten, it shouldn't have any argon in it. But once the rock has solidified, it forms a crystal lattice. That crystal lattice can contain some amount of potassium-40, as well as calcium-40 as well. Now, when that potassium ion atom decays and transforms into argon, that argon atom is trapped. These atoms no longer move or flow in any way that would let the argon out. So after the rock has formed, argon can start to accumulate. And in fact, any argon you see in a rock like this must have been there since the rock solidified. So this makes argon-40 a way to figure out how many potassium atoms have decayed since this rock became solid. Just to give a cartoon example of how that logic works. Let's say we had a rock today and it has 10 units of potassium-40, 1 unit of argon-40, and 12 units of calcium-40. This could happen. Now, the fact that there's argon in the sample today means that some amount of potassium-40 has decayed. And in fact, we can actually figure out how much. Remember, only 1/10 of the potassium decays into argon. So what we can infer is that when the rock first solidified, it contained another 10 units of potassium-40. 1 of those units transformed into argon-40, 9 of those units turned into calcium-40. So we can reasonably infer that the original rock had 20 units of potassium-40. The rock today has 10 units of potassium-40, so half of the potassium-40 has decayed. This rock is 1 half-life of potassium-40 old, which corresponds to about 1 billion years. Now, this is a simplified example. In practice, you have to do a whole bunch of careful things to make sure you're measuring things right. But this is the basic logic of how we can use the composition of a rock to figure out how old it is. And it's these basic techniques that were used on both the rocks on Earth and the moon to make plots like this, which show the relative frequency of different ages. And remember, the rocks on Earth date back to about 3.5 billion years. The rocks on the moon date back to about 4.5 billion years. There's a few rocks on Earth that are 4.5 billion years old. These chondrites, When you do this same measurement to them, you find that they are all around 4.5 plus billion years old. They are the oldest solid objects we have ever been able to measure the age of. They are older than any terrain on the moon and any terrain on Earth. And there's even a little more detail we can get from this. Different parts of these rocks can have different ages. In particular, there are certain things in these rocks called calcium aluminum rich inclusions. They're little blobs of rock that happen to be rich in both calcium and aluminum. These things turn out to be uniformly almost always the exact same age. This is age measured in millions of years. So this is 4.57 billion years ago. This is 4.565 billion years ago. These things are all more or less 4.567 billion years old. Pretty uniform. Now, by contrast, the chondrules, these little beads of rock, have a range of ages. Some are about as old as the calcium and aluminum rich inclusions, but others are a few million years younger than that. What this tells us is that these different things that were assembled into chondritic meteorites were being put together or first solidified within a few million years of each other, at a time that's apparently before the Earth and the Moon's first rocks formed, at least the first ones we can see. Now, in addition to these particular types of objects, there are other types of objects, these iron meteorites, these meteorites that are a mix of rock and metal. There are ones that are made of rock but don't have these little grains, these little chondrules. What these are thought to be are from differentiated meteorites or differentiated asteroids. The idea is you make something originally out of this kind of chondritic matter. What will happen if it's big enough is the insides will get hot. And what that'll allow to do is the metal will separate from the rock, forming a dense metallic core surrounded by a rocky layer and maybe some intermediate mixed level. If these get broken up, you can have meteorites that are pure iron, different types of rock, and different mixtures of rock and metal. And we actually know a few of the asteroids that are in this class. In particular, this asteroid, Vesta, has pretty unique spectra. This is the spectrum of Vesta. And we have meteorites with very much the same spectra. So we have samples of meteorites whose rock composition has changed. There are also potentially asteroids that seem to have high densities, indicating they're made out of mostly metal. Psyche is one of these possible objects, which might be the core of one of these early forming objects. This is what the Psyche mission is going to look at. These objects are range in age by quite a bit. Vesta is a little older, or sorry, a little younger than chondrules, but it overlaps them. It's mostly between about, so these are all times measured relative to when these calcium and aluminum rich inclusions were formed. The parent bodies of iron meteorites, chondrules, and Vesta's core, which is this differentiated asteroid, all look to have formed within about 10 million years of each other. So small bodies had assembled themselves and formed these objects within a few million years of each other. Earth and the moon probably didn't finish assembling themselves until about 100 million years later. So this gives a sense that some of the earliest material, at least the earliest solid material, was small, and that it progressively grew to bigger and bigger things. Now, this brings us to the question of how did this whole system form? How did the sun come to have this particular configuration of planets and asteroids and comets, etc.? Now, one thing I want to say is the answer is fundamentally complicated. Every single one of the planets has its own history. We already talked about how the moon was likely created by a giant impact. There are weird aspects of a lot of these planets. For example, Uranus has a strong tilt, which might be due to another impact. Neptune may have captured a moon from the Kuiper Belt. So there's a lot of individual details that go into the history of every single one of these bodies, which we just can't get into. What we wanted to do instead is discuss the general framework for understanding how the solar system formed, which is what's called the solar nebula model. The idea here is that the solar system, including the sun, formed from a diffuse cloud that was made primarily of hydrogen and helium, but also contained other elements like rock, ice, and some amount of metal. That cloud of dust and gas, because of its own gravity, began to collapse because every molecule in that cloud, every bit of solid matter, is attracted to every other part. This caused it to compress. As it came in, that cloud became denser and denser. At the very center, where most of the material is reaching, a star forms. Surrounding that star, though, is a disk of debris that arises from the fact that this cloud might have been rotating a little bit. We'll talk about that in a second. That debris around it eventually gathers together and coagulates into first small objects like asteroids and maybe comets, and then a few of those get big and grow all the way to planets. This is the basic picture of how our solar system formed. And it's kind of the one you'll see in most textbooks. It is consistent with a lot of the observations. But rather than just say that, I want to demonstrate that by considering an alternative. There is an alternative to this model, to the solar nebula model, which I think provides a useful counterpoint. This is not a widely accepted model, but it allows you to see the strengths of the solar nebula model. The alternative is a class of models called catastrophic models. In this case, the sun forms first as a distinct object. The sun spent some time without planets, but then another star crashed into the sun that collision produced debris that swept, that formed a disk around the sun, and that debris from that collision produced planets. Now, this, just to say, this is not a widely accepted idea for a variety of reasons. And these are simulations of the moon forming impact, because there aren't many simulations of forming the solar system in this way. The thing about this idea, though, is it is at least as good as the solar nebula model for explaining one aspect of the solar system, which is that the solar system has a very distinct architecture. That is, all of the planets orbit the sun in the same direction. And also, all of those planets orbit in more or less the same plane. Now, this is often treated as a point in favor of the solar nebula model. The basic idea is that this is a natural consequence of a contracting cloud. The idea is this: if that cloud has any rotation at all, as the material falls in, it will start to rotate faster. This is due to a conservation of angular motion. It's the same reason if a figure skater pulls in their arms, they start spinning faster. This happens to any cloud. As it contracts, the speed at which the material is moving goes up and up. This basically selects out a direction. So if the cloud is rotating slightly, the material can fall straight in along the axis of rotation to form the sun, but material trying to fall in perpendicular to the axis of rotation starts to end up orbiting that planet because it eventually just is moving too fast to fall any further. This works and makes perfect sense. But this also works for a catastrophic model. As long as you don't hit the sun, straight on, if you hit it slightly obliquely, you will kick off debris in one direction. This will naturally produce a disk of material all going around the star in the same direction, just as well as this does. So that aspect of the solar system is consistent with both of these models. We need other ways to differentiate them. And fortunately, we have those. And if we just consider the solar system itself for a moment, there's a couple of different ways we can distinguish these two models. First of all, we can consider the composition of the sun versus the composition of the solar system. In a nebular model, the sun and the solar system are all basically from the same cloud. So what you would expect is the sun to be made of the same stuff as the rest of the solar system. In a catastrophic model, that's not necessarily true. Just like how the moon has a different composition from the Earth because different materials were scattered in different ways, a catastrophic model could have significant differences between the composition of the objects in orbit around it and its own composition. Also, we can ask, is the sun the same age as the rest of the system? In the nebular model, the answer is again, yes, because they're both forming from the same process. In this case, though, we're assuming the sun formed first. So the sun has to be older than these other systems, than the system surrounding it. And these are things we can do, we can actually measure. Now, composition we've already talked about. The atmosphere of the sun has a whole bunch of lines which tell us the relative amounts of different elements. We have these rocks, these chondritic meteorites, which also we can measure their elemental composition and make a plot like this. This is a plot showing the relative amounts on a logarithmic scale of the different elements. The red diamonds are the values measured from the sun's atmosphere. The green pluses are the values from chondritic meteorites. Now, and they're all referenced to basically silicon. So silicon is forced to be the same. Now, you will see some differences. In particular, the sun has much more hydrogen and helium, and also more argon and other noble gases than chondritic meteorites. That makes sense. Again, things like helium and argon don't chemically bond, so they can't stay inside a rock, whereas the sun is hugely massive, and so it can hold on to that stuff. This also goes for things like carbon, oxygen, and nitrogen, which are things that are easily vaporized and lost from small bodies. But if you look at most of the elements, like sodium, magnesium, aluminum, sulfur, phosphorus, potassium, calcium, iron, nickel, zinc, zirconium, even things like ruthenium, barium, they match remarkably well. This gives us evidence that the composition of these meteorites is very close to the composition of the sun, which is definitely a point in favor of the nebular models. Didn't have to be true for catastrophic models. You could maybe make it work, but it's definitely not. If there was a clear distinction, then that would be a point in favor of these models, and we don't have that. Okay, what about the ages? Well, we already talked about how we measure the age of these material, of the first solid matter in the solar system, and it works out to be about 4.5 billion years. Well, we can also estimate the age of the sun. Now, we'll talk about this more in the next section, but the sun is basically a gigantic nuclear reactor that is converting hydrogen into helium. So as the sun ages, it becomes more and more helium rich, which affects its density, structure, and various other aspects, which can be measured using sunquakes, essentially, which give a measure of the total amount of stuff in the sun and how it's distributed. Turns out that you go through that math, the sun is about 4.5 billion years old. So the oldest solid materials in the solar system is about as old as the sun, which is, again, consistent with the nebular model and not what you would have predicted from the catastrophic models. So this is why, for a long time, the nebular models have held most of our attention. Now, that's just thinking about our solar system in isolation, though. We can get even stronger evidence for the nebular models if we consider other planetary systems. The thing is, these two models make very different predictions about how often stars should have planets. In a nebular model, you would expect sun-like stars to often have planets, because all you need to produce that disk is a slight rotation in the gas cloud. So this process means that most stars that form probably will have planets associated with them. Maybe some won't, maybe some will, but it's a common fraction. It won't be rare. By contrast, since stars are widely separated objects, remember the distances to stars is really big, collisions are rare. So if you're talking about catastrophic models, you do not expect most stars to have planets because they wouldn't have had a collision to produce them. Now, the fact that you need to have a collision before we would exist means that we would be on one of the rare stars where it did happen. Well, we'd be orbiting one of the rare stars that did happen, but it would mean that planetary systems would be comparatively rare. So this is a real distinction here. And the evidence is planetary systems are common. We can now look at stars in the act of forming with various instruments. These are images taken by the Hubble Space Telescope of several young stars, each of which is surrounded by a disk of debris. These are radio images of various young stars showing more structured disks. These are common. These are not rare or hard to find things. So disks around young stars are common. And planets, now that we found thousands of them, are also common. By looking at how many detections people have made, we now know that for stars similar to the sun, about 10% of them have planets, with a fair error bar on that. But what that means is a lot of stars have planets. They're not rare. By contrast, if we were talking about catastrophic models as the primary way to make planets, we would expect more like a fraction of 1 in 100,000, not 10%. And of course, this is based on the planets we can see. There are caveats on all of this. So the recent discoveries of exoplanets and other planetary systems are what give us a lot of evidence or a lot of confidence that solar nebula models are sensible framework. At the same time, it's worth noting that exoplanets have also led us to challenge certain aspects of those models. When we had our solar system as the only example of material orbiting a star, we noticed that we had rocky planets close to the star and gas-rich planets further out. This was thought to be a natural consequence of solar nebula models, because it turns out that you really have to form a giant planet, a planet that's composed primarily of hydrogen and helium, like, say, Jupiter and Saturn are. You have to form them quickly. Remember, it took about 100 million years for the Earth to finish being built. That was when the moon formed, which was probably the last major impact. The giant planets Jupiter and Saturn have to form before that. They have a very short amount of time to form because they are made of hydrogen and helium. Now, hydrogen and helium do exist in the protoplanetary disk, but they don't last very long, because as the sun turns on, as the material falls into the sun ignites and starts shining, that radiation will blow the hydrogen and helium out of the solar system. And we have measurements of how much the gas disk survives as a function of age. And it turns out that the typical lifetimes of the gas disk is only about 5 million years. So if you want to make a gas-rich planet, you need to make it in that kind of time frame. If you try to make it any later, there's just no hydrogen or helium available to make them. Once it's collapsed down into a planet, it's in the planet's gravity well. The solar radiation just heats up the planet. It doesn't disperse it. So that suggests that the giant planets formed more quickly than the terrestrial planets. And there was a good reason to think that this might actually be the case. The thing is, Jupiter and Saturn formed further from the sun. Okay, why does that help? Well, if you're far from the sun, it changes what materials are available to make solid things from. If you're close to the sun, the only thing that could ever be a solid is metal or rock. And so your solid components are made of those. Those things can stick to each other, begin to grow into asteroids and planets, etc. Turns out there is much more water in astrophysical disks than anything else besides hydrogen and helium. If you're outside a certain distance, water can freeze into ice. So in addition to being able to make particles of, say, rock and metal, you can also make particles of ice, which can coagulate and start forming planets, etc. This happened, being out that far, where Jupiter and Saturn are, that allows that to happen. Jupiter and Saturn could have been thought to have been formed around cores that were ice-rich, which grew faster than the planets were being assembled in the inner solar system, and so were able to glom on to enough hydrogen to be their current state. So that would naturally produce giant planets outside the terrestrial planets. And so we naturally thought that high mass planets like Jupiter, Saturn, maybe also Uranus and Neptune, would naturally be found further out, and low mass planets like Earth and Venus are found closer in because they just didn't have the resources to grow as big. So this is a plot showing planet mass as a function of orbit period, which is also semi-major axis. What you will notice here is these points are all the known exoplanets. There are a large number of high mass planets comparable in mass to Jupiter or Saturn that are very close to their host star. They orbit even inside the orbits of Mercury. Does this mean that maybe these planets formed like Jupiter and Saturn, we think did, and then moved inward? That's an option. Alternatively, were the disk conditions different in the disks that produce these planets than the ones that happened here? Maybe giant planets can form close to their host stars under appropriate conditions. This is actually something that's still a subject of active debate, and shows how considering more than one system can start to reveal things that you had previously not been aware of. Okay, thanks much for your time and attention, and I'll see you all in class.